Hello all, this is Christine and I'm going to be your host through fluid and electrolyte balance, acid-base balance, and what to do about it. I'm kind of combining chapter 45 in McKinney, concepts 7 and 8 in Giddens, and other information that I thought was important. So hopefully this will help you guys out with the whole acid-base balance nightmare, which I always found very difficult in nursing school. Okay, so first we're going to talk about what fluid and electrolyte balance is. It's the process of regulating the extracellular fluid volume, body fluid osmolarity, and plasma concentrations of electrolytes. All right, so extracellular meaning outside the cell. Body fluid osmolarity is also usually tied in with sodium concentration, and plasma concentrations of electrolytes, pretty self-explanatory. All right. We're going to first review some physiology, and I'm getting my notes here so I don't forget anything. All right. We're going to start with the kidneys and move our way down the urinary tract. We have the kidneys that are considered our most important organ of excretion. They're here. There's two bean-shaped kidneys in our bodies, and the right is a little further down in their peritoneal cavity than the left because you have the spleen pushing on it. They are in the posterior aspect of your abdomen in the flank area in the retroperitoneal cavity behind behind the peritoneal membrane. They're protected by your ribs, your renal fascia, and adipose tissue, thick pad of fat, which is all around the kidney. Okay. They are responsible for excreting waste in our body, and they're the most important organs of excretion in our body. They eliminate water, nitrogenous waste, electrolytes, toxins, and drugs. They regulate erythropoietin excretion. They regulate acid-base balance. Let's see, am I missing anything? Okay. So they also, by regulating water content, they regulate your blood volume and therefore your blood pressure. So you have these two kidneys, and leading from the kidneys you have your ureter, which is basically a transportation device for urine down to your bladder, which is basically a storage collection device for urine to your urethra, which is the tube going out to your toilet, hopefully. And don't confuse your urethra with your ureter. They're two different things. Urethra is shorter in a girl, and that makes you females more prone to urinary tract infections. When you have an infection of your kidneys, you get flank pain because of the location of your kidneys, and you can also even get back pain from that infection. And the infection of the kidneys is called pyelonephritis, and is very painful. Usually it takes several days of antibiotics before the patient stops having fever and pain, and you're going to use like anti-inflammatories and antibiotics, but we'll move on to that later on. So your kidneys perform the essential function of removing waste products from your blood and regulating water fluid levels. Those are the two biggest. The diagram below shows the basic structure, and I'm going to move on to here. We have the three main portions: the medulla, your cortex, and your renal pelvis. Your medulla is made up of these renal pyramids. You have 8 to 18 in each one of your kidneys. Sorry, that's my dog. And you have the renal cortex, which contains the top of your nephron, your Bowman's capsule, and your glomerulus, and then this bottom portion contains the loop of Henle and collecting ducts. And all of that drains down into the renal pelvis, where the urine flows from the proximal ureter down into eventually your bladder. Alright, so you have, at any given point in time, let me switch this here. We're going to erase this. At any given point in time, you have 5 liters of blood in your body, and your kidneys at any given point in time have 20% of that. So you have about 1 liter of blood flowing through your kidneys at right now, as I'm speaking to you. And when we talk about blood flow to our kidneys, we need to start with cardiac output. Cardiac output, if you remember, is basically your heart rate and your stroke volume. So cardiac output is the total amount of blood being pumped out of your body, and that's reflected directly by how often your heart is beating, which is your heart rate, and how well it's contracting, which is your stroke volume, how much blood is being pushed out. So those two factors together equal cardiac output. Your blood pressure is simply your cardiac output times the resistance in your arteries. Alright, so that's why when you have arteriosclerosis and your arteries start getting hardened and you get buildup in your arteries, your blood pressure increases. So why does this concern your kidneys? First of all, anything that affects how much blood you have in your body is going to affect your cardiac output. So if you get dehydrated, your blood volume goes down. Here's your blood volume. That's going to lead to a decrease in cardiac output. That was a bad arrow, but okay. And that's going to lead to a decrease in blood pressure. And that's going to lead to a decrease in flow in blood flow to the kidneys. And that is going to lead to a decrease in urine output. So anything that affects cardiac output is going to eventually affect urine output. And in fact, that one should be the first sign that you look for when you are looking to see how dehydrated your patient is. Or if your patient is dehydrated, look at their urine output. Also, if you have a patient that you suspect could be in any form of shock, first thing you want to take a look at is their eyes and nose and their urine output. Okay. So moving back to the kidneys here, we have the functions. They excrete nitrogenous waste, and they get rid of toxins and drugs. I'm just going to put toxins and drugs here. All right. Maintain acid-base balance. And they regulate the amount of water. I'm just going to put regulate H2O. They regulate electrolytes. And they stimulate erythropoietin production. And we're going to talk about all those in a minute. I can't spell. That's probably not how you spell erythropoietin. Did I forget anything? nitrogenous, toxins and drugs, maintain acid base, regulate H2O, they regulate electrolytes, and they stimulate erythropoietin. Okay, I think we're good. So here is our recording pad. Alright, so here we have the medulla, the renal cortex, and the renal pelvis again. And your kidney is being fed by your renal artery. This comes directly off of the aorta. And then you have your glomerulus here, which is a bed of capillaries, and your Bowman's capsule. And this is all part of your nephron. This whole thing is your nephron, and you have millions of nephrons in each kidney. And they act as tiny filters that take blood, and when the process is over, you have urine. So the first part of your nephron, this glomerulus here, is just a bed of capillaries. And what happens is you have a flow of blood into this bed of capillaries, or this glomerulus, and this blood gets pushed out. The force of the gets pushed out into the Bowman's capsule. And what happens is red blood cells and large proteins are left in the capillary bed, and the electrolytes and water, glucose, and so forth gets pushed into the Bowman's capsule. And I'll explain how that happens in a moment. You have this little arteriole here is called the afferent arteriole, and this is called the efferent arteriole. So, and like most organs that have an artery coming in and a vein leaving, the kidneys have an artery coming in both ways. And it has smooth muscle that constricts or expands based on the volume of blood into and out of the kidney. So here we have a valve in each arteriole, and the valve in the afferent arteriole acts like like a faucet with a hose attached to it. You turn on the faucet, you allow in the flow of blood. The valve on the efferent arteriole acts as the nozzle. So you push down on the nozzle, you let the blood flow back out. What happens if you don't let the blood flow back out? You end up with renal damage. So if there's anything wrong with these valves, if the kidney is damaged in any way, you end up with kidney damage. Okay, so let's talk a little bit more about how this all works. So we have here, this is your capillary of your glomerulus, and on your capillary, lining your capillary right outside it, you have these fenestrated cells. And fenestrated simply means that there's little holes in the capillary, in the cells lining the capillary, and that allows the movement, as we were talking before, of electrolytes and water out of the capillaries. But it is not large enough to let red blood cells and proteins out. These holes are also very highly charged, and that helps hold in the protein and red blood cells. And then it flows past these cells here called podocytes. This is all filtrate, and then goes into the Bowman's capsule. Okay? So the basement membrane is this fine mesh that restricts the passage of blood cells and proteins. It's the sole filtration barrier between the capillaries and the Bowman's capsule. The blood can exit the glomerulus directly through pores as the capillaries are fenestrated, or they have holes. And the filtrate can enter the Bowman's capsule directly because the podocytes that surround the glomerulus contain slits. All right. The basement membrane lies between the glomerulus and the Bowman's capsule. So this is pretty neat. A little way here of it's basically like a coffee filter, if you can imagine that. And this is the coffee. This is your filter, and when you're done is drinkable coffee, or in this case, urine that can be excreted. So at every given point in time, you have about a glomerular filtration rate of about 125 milliliters per minute, based on that 1 liter of blood that's coming in your kidneys. Okay. Alright, so let's move on to the next slide. This is just another view. Here's the capillaries, and we have the endothelial cells here, endothelium, and these little fenestrations that allow, basically just holes that allow electrolytes and water to come through the basement membrane and then to the Bowman's capsule. This is a long view of what this all looks like. So here you have the glomerulus right here, and then this is the Bowman's capsule, and all of these tubes here we're going to talk about the proximal tubule, the proximal convoluted tubule, leading down to the descending loop of Henle, ascending loop of Henle, distal convoluted tubule here, and then the collecting duct. So this whole portion, this is where is the cortex, and then this portion is the medulla. Okay, so if you were to insert a device into your kidneys and test the pH, it's going to be very different up at your cortex than it will be at medulla, and we'll explain why in a minute. All right, here's a close-up view of what a nephron looks like. Here's the afferent arteriole and the efferent arteriole, and then as you can see, once that efferent arteriole leaves, it doesn't just go, back to the renal artery or anything. It wraps back around, comes back and the flow of blood goes this way. Okay? So what happens is, we'll talk about this a little more. Here's the flow of blood, and it joins back up in several places, here, several places to the nephron. And so the flow of blood in the nephron is going in the opposite direction, or it's not blood actually, it's filtrate. And I'll explain to you why this is important in a second. So basically though, here's all the filtrates coming into the Bowman's capsule. It flows through the proximal tubule, the proximal convoluted tubule. Proximal meaning closest, and convoluted meaning twisty, that's all. And then flows through here to the distal convoluted tubule, distal meaning for far away, convoluted meaning twisty again, to the thick ascending, to the collecting duct. Alright. So the nephron has different functions for each portion of it. So here in the proximal portion of the tubule, you get reabsorption of water, ions, and organic nutrients, and it's very permeable to water. And then as we come down here, the proximal, or the descending limb of the loop of Henle, it's still very permeable to water. And then as it comes back up, it gets less so, and then by the time it reaches here, it's not permeable to water anymore, and I'll explain why that's important. So here we have this portion of the nephron, the Bowman's capsule, and the glomerulus. we have sodium, potassium pumps that are basically driving through primary and secondary pumps. And these potassium and sodium that's leaving here, this is a lot of potassium and sodium leaving. It's driven by ATPase pump, so it takes energy for this process to occur. All right. In the proximal convoluted tubule, well, sorry, this portion here, water follows the solutes, and the osmolarity of the fluid is equal to plasma. Okay. So right here, the osmolarity is about equal to plasma. Then it continues on, and then as we get into, I have so many notes here, I want to make sure I'm getting everything right. Alright. So here is the hairpin turn in the loop of Henle. Sounds like something out of NASCAR. And what happens is, as it becomes less and less permeable, you start to have a big change in osmolarity. So this portion here is isotonic. Its plasma is equal, the osmolarity of the fluid is equal to the plasma. But then as we get up here, it becomes more and more hypotonic. And what happens, we'll show in the next slide why. Alright. So here is the first kind of step. Did I get this? Okay. So we have the osmolarity. This is the descending loop of Henle, the hairpin turn, and the ascending loop of Henle. The osmolarity is about equal. All right. Now, there is a natural tendency. We have water flowing out, and once we get up to here, here's our capillary bed. The flow is in the opposite direction. Once we get up to here, the osmolarity starts changing, okay? And so much, because the flow is in the opposite direction and water is getting pulled into here, pulled into here, pulled into here, pulled into here, and it starts out pretty concentrated. By the end, it's getting more dilute. You end up with a reverse. So for here, it's more concentrated and it gets more dilute, and here it's more concentrated and gets dilute in the opposite direction. So you end up 300, 300, and 300, because by the time you get, this is the start of the flow, blood, or the potassium and sodium are going to naturally flow into the capillary bed and make it more concentrated. So it kind of is reverse effect. This flow going this way has the effect, by the time it gets up to here, so much water has been pulled out that the concentration, you would think, would be greater. But in fact, because